today we're going to look a little bit more at the Flory-Huggins parameter and also talk about issues of stability, metastability, and instabilities that may arise when we start to mix different components together. So two polymers, polymer and solvent, or even two different solvents. So the important result that we came to last time was that we can kind of group all of these interactions or these energetic terms into a single parameter called chi, and chi is dimensionless. And it was defined as the coordination number divided by 2 kBt. So remember, kBt has units of energy. And then it was multiplied by a term that looked at the differences in the strengths of interactions between particles that were the same type and particles of different types. So this was equal to 2 times UAB minus UAA minus UBB. And remember also that these U's, so UAA for example, these are all less than 0. So how do we use this? Well, I said last time, if we're going to do a computer simulation, we will know what these interaction strengths are because they're things that we specify. So I get to tell my polymers with what strength they're going to interact. But experimentally, of course, I don't have that control necessarily. And I don't know that I can necessarily measure all of these different components. How would I know what UAA is, what UBB is, etc.? So typically, experimentally, what I do is I measure just chi. So I get this dimensionless number chi that tells me something about the interactions. We'll talk in a little bit about how we might measure chi, but as you might guess, scattering is going to play a very important role in how we measure it. But that's not the only way that we can start to get at what these values are for the interactions. One way that we can do this is we could look at a system. I think A was blue, but if it wasn't, then forgive me and make the appropriate substitutions as necessary. But let's look at a system that is all A. So this is all A particles in here. And let's look at just a single A particle in this system. And what's going to happen? Well, if it's in a system by itself, it's in the unmixed state, and it's just by itself, and it's interacting with all of its neighbors that are the same type. So this particle might interact with its 4 nearest neighbors. And of course, in reality, there are going to be more than 4 nearest neighbors, but for simplicity, let's just look at that case. And so this would be Z equals 4. Now, how might we look at this system so that we can get an estimate of what UAA might be? Well, one thing that we could do is we could calculate how much energy does it take to vaporize that particle. How much energy does it take to completely remove it out of the condensed phase and put it into the gaseous phase? So this is going to take a certain amount of energy to vaporize it. And that difference in energy is going to be the difference between having no A particles up here to interact with and the situation in the condensed phase where that particle is interacting with its Z nearest neighbors. So this delta EA is going to be the energy it takes to remove the particle from its neighbors, to remove a particle from its condensed pure phase. So energy to remove, it's actually the energy to vaporize, but it's also removing the particle from the unmixed or pure state. Okay, so we could look at an energy density. We could define an energy density as that energy that it takes divided by the volume of that A particle. And so this is an energy density. I think it's a cohesive energy density. And we're going to define something from this. We're going to define what we call a solubility parameter. The solubility parameter for A will be equal to the square root of that energy required to remove it from its condensed phase divided by the volume of the A particles. So I could also do this for B. I could define that the solubility parameter for B would be the square root of the energy it takes to remove it from its pure unmixed state divided by the volume of a B particle. Okay. So how does this relate to chi? Well, chi, again, is equal to Z divided by 2 kBt times 2 UAB minus UAA minus UBB. So let's just look at one of these terms. Let's just look at the A term. So let's just look at this term, for example. Remember, UAA is less than 0. So if I wanted to get an idea of what the energy is, well, if I have minus Z times UAA divided by 2 kBt, that quantity should be positive, and that's the interaction strength of an A particle with one neighbor multiplied by the number of neighbors that there are, of course divided by 2 so that we don't double count. Well, that should be equal to delta EA divided by VA. That doesn't have the right units. That's an energy density. So we need to multiply by the volume of a lattice site, and that will give me a measure of what that interaction strength is, right? And this is the same thing as V0 times delta A squared. So you can see very clearly that if I wanted to, I could solve for UAA as minus 2 kBt V0 delta A squared divided by the coordination number. So I could do that for B also if I wanted. So I guess I will also just write it for completeness then, that minus Z times UBB divided by 2 kBt would be V0 delta B squared by the same argument that I just made. So what about the cross term? What about an interaction between A and B? So minus Z UAB divided by 2 kBt is equal to what? Well, we can make an approximation. We could approximate this as being a geometric average. So we could approximate this as being V0 times delta A times delta B. And that would be the same thing as V0 times the square root of delta EA, delta EB, divided by VA, VB. And I could do the same thing. I could solve for UAB, and I would get minus 2 kBt V0 delta A delta B, and then divided by the coordination number. So I can substitute these into the chi parameter, and I can get a useful result from that. So if I just directly substitute these in, I've got that chi is the coordination number divided by 2 kBt. And then I'm just going to substitute in for UAB, UAA, and UBB. So I've got 2 times minus 2 kBt V0 delta A delta B divided by Z minus 2, make sure I don't screw this up, kBt V0 delta A squared divided by Z, and now I just need to substitute in for UBB. So minus 2 kBt V0 delta A squared divided by Z, and now I just need to substitute in for UBB. So minus 2 kBt V0 delta B squared divided by Z with a minus sign out front. And you can see that a number of things are going to cancel and that V0 is going to be a term that appears in each one of the three energetic terms in the brackets. So what I'm left with is 2 kBt will cancel out with 2 kBt, 2 kBt, and 2 kBt. Z will cancel out with the coordination number in each of those terms. And V0 is common, and I can pull it out. So I can pull this term outside of the brackets. So what I'm left with for my chi parameter is I've got V0. Actually, I made a mistake here. There should be no kBt in these fractions. So this term shouldn't have it. This term shouldn't have it. I took too many things inside. What else? I think this about fixes it. Okay, so if you did that, make sure you take those terms out. I don't quite want to do that. So let me fix the equation for you. Okay, that's the correct expression. And so I don't want to cancel out kBt. But what I do want to cancel out is the 2. So that 2, that 2, that 2, and that 2 will go away. Sorry. Okay, so I pull V0 out of those brackets, and I've got kBt in the denominator. And what I'm left with inside the brackets is going to be, here a minus and a minus will give me a plus. So I've got delta A squared minus 2 delta A delta B plus delta B squared. And you can see that that's just delta A minus delta B squared. So this is equal to V0 divided by kBt, delta A minus delta B squared. And that is chi. It's not all of chi actually, but that's a point that I'm going to revisit in a second. So there's a couple of caveats here. You see that because of the way this expression is written, this chi parameter will always be greater than 0. So for this expression, it's implying that chi is always greater than or equal to 0. And as a result, that means that this is always predicting that things are tending to demix, especially with polymers, right? Because the chi parameter we'll see for big polymers, if it's greater than 0, you're going to start demixing. So this is not taking into account H bonding. So there's no hydrogen bonding. And no polar interactions. So it's not the complete story. We could also group this together. You can see I've got a term that looks like this that doesn't depend on temperature. They're more or less just constants. So I could also write this chi parameter as B divided by T, where B is equal to everything in that box. That's great. So what can I do? Well, I can already see that this means that chi is going to have some kind of temperature dependence. So assuming that I can measure the temperature dependence of chi, which I promise that I can, I could plot that temperature dependence. And you can see that since T is in the denominator, it might make sense to plot this as 1 over T. So 1 over T, if 1 over T is small, then that means that T is big. So this end of the graph is at high temperature, and this end of the graph is at low temperature. So I can go out to my lab, I can take measurements of the chi parameter at various temperatures, and I can plot them. And what I typically find is something like this. So the relationship between chi and 1 over t tends to be linear. Again, it doesn't always have to be linear, but it tends to be. And what this is telling me from this graph is that interactions are less favorable at low temperature, right? Because the chi parameter is increasing as I lower the temperature. Or the same thing would be saying down here that interactions are more favorable at high temperature. And that's kind of what you're used to. Let's say I want to dissolve a lot of salt in some water, or a lot of sugar in some water, or something like that. Or, hell, I want to dissolve polystyrene in toluene. Well, what do I typically do if I want to dissolve more things? Well, I typically heat it up. And you've seen probably for the last 20-something years of your life that if you want to dissolve something, you typically heat up the solution, the solvent, put in what you're trying to dissolve, and it dissolves better at higher temperatures. That's not always the case, though. So it is possible that you could measure a system like this, and you might find a slope like that. You might find that the slope is negative on this graph. And what this is saying is that interactions are less favorable at high temperature. And of course, the opposite at low temperature. And someone sent me an email about this the other day, and it was a great question. And the question was, if I have something like polystyrene in toluene or cyclohexane, if I heat up the solvent, so if I heat up the cyclohexane, the excluded volume of my polymer chain becomes positive, and it becomes increasingly positive as I heat up the solution. A result of this is that my chains go from being ideal to being swollen chains because interactions are becoming more and more favorable. But the question that I received was specifically about polynipam. And polynipam is known to undergo what's called a coil to globule transition when it's above a certain temperature in water, and this temperature is about 32 degrees C. So what this is telling us is that for a system like polynipam, as I heat up my solution, the interactions are becoming less favorable between the polymer and the solvent, and the excluded volume is decreasing. So a coil, let's say an ideal coil, will have an excluded volume of 0, and when I go through this transition temperature, I'll form a globule, and a globule is going to have an excluded volume that's less than 0. So I'm going to have an n to the 1/3 scaling for the size of that globule. So what this means is that interactions are becoming less favorable as I heat up my solution. And there's a specific reason that polynipam does this, and we'll talk about it in the next couple of videos probably. But it's just an example that this is not always true. So whereas if you want to dissolve polystyrene and cyclohexane, you will heat up your solution if you want to get more stuff in there. If you wanted to dissolve polynipam more effectively in water, you would put your vial into the fridge or into the freezer to cool things down, and it will dissolve better in that case. So we can summarize these types of behaviors by writing that the chi parameter, because you can see that there could be a y-intercept in this linear plot. So the chi parameter as a function of t, we can write usually as a plus b over t, where, and sometimes we might have to include more terms. But for most systems, or for a lot of systems, this expression is sufficient. And you can kind of see why this is plausible, because at least for the chi parameter in terms of the solubilities parameters, we saw that we get this b over t form. Okay, so what this also means is that we can write the chi parameter as a sum of energetic terms and entropic terms. Okay? Which is which? Which one's energetic and which one's entropic? Well, let's go back to our free energy of mixing. So it's kBt, all of that entropic stuff, plus chi times phi a times 1 minus phi a. So let's just look at chi, because the volume fractions are just the volume fractions. We will discuss what the volume fractions mean later. But if we just look at delta F mix as including, or at least for a polymer, those entropic terms are about 0. So if this is approximately equal to kBt chi phi a 1 minus phi a, how would we figure out which term is entropic? Well, we could go back to our Maxwell relations, and we know that delta S would be equal to minus the derivative of delta F with respect to temperature, holding everything but temperature constant. And actually, if this is everything but temperature, let's just ignore that volume fraction term for a second. And we could see that for the entropic part, we would have that the entropy would be minus the derivative with respect to temperature of kBt times A plus B over T. And so I can multiply through by temperature. So minus the derivative with respect to temperature of kBt times A plus KB times B. And I think you can see very clearly that this is just going to give you minus KB times A. So this means that the entropic part of chi is what we call A. Or A is what we call the entropic part of chi. So that means that the other term has to be the energetic term. The other term would be B. I don't like just taking that as the answer, though. So how would we show that that's the case? Well, we could go back to the Gibbs-Helmholtz equation. From last semester. And what did that tell us? It told us that the derivative of delta F divided by temperature with respect to temperature was equal to minus U squared over T squared. And for completeness, I'll just say it also told us that the derivative of delta G divided by T with respect to T was equal to minus delta H squared divided by T squared. Okay, so we go back here and we look at what delta F is, and we've got that expression. So if we divide it by T, then that T is just going to go away. So what is the derivative with respect to temperature of Kb times A plus B over T? Well, Kb times A, that's a constant. That'll go away, and we'll get minus Kb times B over T squared, which is minus delta U squared over T squared. And I think there's a factor of... No, it's fine how it is. Okay, so you can see that B is the energetic term. So the energetic portion is equal to B. So what does this mean in terms of the solubility parameters? Well, it means that the chi parameter is, again, the energetic portion plus the entropic portion. We saw that B is the energetic portion, so this means that this is V0 divided by kBt times delta A minus delta B squared plus the entropic part. Does that make sense? It kind of makes sense, right? Because where do those solubility parameters come from? They come from measuring the difference in the energy of the particle being in its condensed state with all of its friends and being out in space all by itself with no friends. So it makes sense then that this would be purely energetic and that we're missing an entropic component. That entropic component, this is typically about 0.2 to 0.3. So a common expression that we have and a common value for chi-s is 0.34. So this means that the chi parameter in terms of the solubility parameters would be equal to V0 divided by kBt, delta A minus delta B squared, plus 0.34. Okay, so that's fine, but remember the limitations of these solubility parameters is that they don't have hydrogen bonding, they don't have polar interactions. So this is not going to be the full story, but if we have something like polystyrene in cyclohexane or polystyrene in benzene or polyethylene in hexanes and things like that, this expression tends to work pretty well. And you can do things like estimate what solvent you expect to be the best solvent for a particular polymer chain. And I'm going to assign a homework problem where you do exactly that. So if you have polystyrene or if you have PDMS, so a silicone, what do you think the best solvent for the silicone will be? What do you think the best solvent for the polystyrene will be? If I give you a bunch of these solubility parameters, you should be able to figure out which one is best. So I'll give you another example, or I'll give you some typical values for these. So for polystyrene, the solubility parameter is about 18.5 megapascals to the 1/2. And hopefully you can see where those units will come from, because you've got energy, so joules. You have a volume, meters cubed. So hopefully you can see that that will give you a pressure for the solubility parameter. And then you take the square root of delta E divided by V. So you've got pressure to the 1/2 power. Chloroform, its solubility parameter is about 19. So you could maybe estimate whether or not you think that polystyrene will dissolve in chloroform. And as I found out, well, I didn't find out because I didn't do this, I knew better, but as somebody that I went to grad school found out, you can't put chloroform into a polystyrene cuvette and then put it into a UV vis, because chloroform will dissolve polystyrene, which is exactly why you put chloroform in the cuvette in the first place, because you were dissolving polystyrene. But anyway, if you substitute these values into the expression for chi, you hopefully will see that it's very likely that chloroform will dissolve polystyrene. And we'll talk about that in a little bit more detail in the next video. Last thing that I will say is that, well, maybe I'll just emphasize it a little more. I just want to emphasize one last time. This chi parameter from the solubility parameters is always greater than 0. So that's going to play a role in whether or not we can predict certain behaviors based on the solubility parameters. But for a lot of things, especially for polymer solutions, it's quite useful. And if you look at just the predictions of this expression for polymer blends, just based on this expression alone, you expect that most polymers will not mix. So we'll have to play some tricks in order to get them to mix together.